How do inlet, outlet, and wall boundary conditions work in CFD? Imagine you're trying to understand how water flows through a pipe or how air moves over a wing. To do this accurately in computational fluid dynamics, you need to set the right boundary conditions. These conditions tell the simulation how the fluid behaves at the edges of the area you're studying. Without them, the results could be off or even meaningless. Let's explore how inlet, outlet, and wall boundary conditions work and why they matter so much in design and analysis. First, think about the inlet boundary condition. This is where the fluid enters your simulation space. You can specify how fast the fluid is moving, how much mass is flowing in, or what pressure it has at that point. For example, if you're simulating airflow into a duct, you might set a velocity inlet with a certain speed. This helps the software understand exactly what kind of flow to expect at the start. Sometimes, you might specify the pressure instead, letting the software calculate the velocity based on that pressure. Getting this right is important because it influences how the flow develops inside the domain. If you set a realistic velocity profile, like a smooth, uniform flow or one that varies across the inlet, your results will better match real-world conditions. Next up is the outlet boundary condition. This is where the fluid leaves the simulation area. Here, you usually specify the pressure at the exit, often set to atmospheric pressure, or you might allow the software to determine the best conditions automatically. Sometimes, you can set a zero normal stress condition, meaning the fluid can leave freely without any artificial constraints. It's important to place the outlet far enough from critical regions so that the flow isn't affected by the boundary. Proper placement helps ensure the simulation remains stable and converges to a solution. If the outlet is too close or not set correctly, it can cause errors or unrealistic results. Finally, we have the wall boundary condition. Walls are solid surfaces that the fluid interacts with. The most common condition here is the no-slip condition, which means the fluid velocity at the wall is zero relative to the surface. This models real-life situations where fluid sticks to the wall, creating boundary layers. Walls can also have temperature or heat flux conditions if thermal effects are involved. Sometimes, surface roughness is included to simulate how textured surfaces influence flow. Properly defining wall conditions is key because they affect flow separation, heat transfer, and overall behavior near surfaces. In practical engineering tasks, like designing piping, HVAC systems, or aerodynamic parts, setting these boundary conditions correctly makes a big difference. They help produce reliable predictions of pressure drops, flow patterns, and thermal effects. If you get them right, your CFD simulations become powerful tools for improving designs and solving real-world problems. Remember, choosing the right boundary conditions depends on the flow type, whether it's compressible or incompressible, and the specific goals of your analysis.